From weak acids to weak bases. Very similar idea. They don't break down completely in water, but they do break down in water. For bases, the weak base reacts with water to give you a conjugate acid of the base and OH minus ions, which OH minus is one of the defining factors of a base. So you take your proton from water, you make the conjugate acid, you make OH. There's my generic. B is my base. Reacts with liquid water, so we're never going to put it in the Kb expression. If it was Ka for acids, it's Kb for bases. Hb plus, that's the conjugate acid, the base once it's gained a proton. And OH minus, the hydroxide ion coming from the base reacting with water. Kb is your base dissociation constant, just like that's the fancy name for Ka, your acid dissociation constant. And there's what your constant Kb. It must be important because that's the third time that's on this page. I got this from the book, Conjugate Acid and OH. I had a tougher time learning to do these base dissociations than the acids for some reason. Even though they're not more complicated, I feel like a lot of times people spent more time on acid neutralization or acid breakdown than on bases also reacting with water. If you draw out the Lewis structures for the bases in your packet, and if you need to hit pause and copy mine are messy, but they're right. What you'll see for these weak bases really commonly is an unshared pair on nitrogen or oxygen, trimethyl ammonia, and yeah, I did the boring CH3 scribble down because it's carbon. It's always going to look the same. I did put the dots on the OH and showed you just some of the unshared pairs going through here for trimethyl ammonia, for hydroxylamine and the acetate ion. It's these features that are going to allow your bases to bond. So with your types of weak bases, you're going to get neutral substances that can accept your protons, like nitrogen, which you can make it take a hydrogen. It's going to be positively charged, but we see with NH3 becoming NH4 plus, the ammonium cation, that that's okay, that it works that way. So you're going to replace the dots with a hydrogen. So in your drawing where we're looking for your product of that reaction, you're still going to have your benzene ring with a nitrogen, hydrogen in place of your double bond. I couldn't type that, so you're on your own there. These anions of weak acids can also be your weak bases because remember, strong acids make anions that are negligibly basic. Same thing with strong bases, but in the middle, weak acids and weak bases pair up. So in your example there, you're looking at an anion of a weak acid gaining hydrogen to form the acid and leaving an OH minus. So let's look at a practice here on calculating your molarity. Once you get to your molarity, you're able to calculate a pH also because your OH value is there. Go to POH and then pH. So I will put that up, leave you my equation here, my basic equation, for dissociation of a base. And I'm looking at a solution of ammonia in water with a pH of 11.17 and a Kb of 1.8 times 10 to the negative fifth molarity. Here we go. Let's write our dissociation equation. I know that ammonia is my weak base, NH3. I know it's going to combine with water, and it's liquid. Normally I'd write the state symbols, but since I'm putting them right under an example, I'm not. NH4. I should. I'd be a good teacher. There we go. Plus OH minus AQ, which means my Kb is going to be my concentration of NH4 plus, my concentration of OH minus, and my concentration of NH3. I'm ignoring water because it's liquid. So I need to find my equilibrium concentration here. My pH is 11.17, so if I do 10 to the negative 11.17, I'm going to be able to get a pH that way. I'm going to be able to get a concentration of hydrogen that way. And I'm going to be able to work backward from there. In the example, I did it a little differently, but they'll both get you the same way. If you look in your packet, I did pH of 11.17, giving me a pOH of 2.83. So then I would calculate my concentration of OH as the negative log of 2.83. What I was headed for here with my concentration of hydrogen was to get that and use 1.0 times 10 to the negative 14th being concentration of hydrogen and concentration of hydroxide. Either way you like that, you're going to get to a concentration of hydroxide ion at 0.0015. I just wanted to take that chance to remind you that there are a bunch of different ways to get to your OH concentration, whichever one you like better. Set up my ice chart. Hoping I'm not running out of room. No, not quite yet. So I've got NH3. A little crowded there. H plus. And, sorry, HB plus. So, better. There we go. And OH minus. I, my initial. And my change. And my equilibrium value. I'm probably going to have to erase up at the top once I get these to show you how I solved it. But I think this one's going to be pretty easy. From my concentration of OH, realize that this is after I've reached equilibrium. So I have a solution of NH3. So I don't know what concentration I started with. But I do know that before I threw it in this water, it hadn't ionized. Not at all. So at the end, when I take its pH, the pH tells me my concentration of OH minus is 0.0015. My pH also tells me that that would be equal to my concentration of NH4 plus. What is my concentration? What was my change? Well, it looks like I've gained 0.0015 here for both of these, which is really nice because I know then that NH3 has lost 0.0015 for a concentration of X minus 0.0015 molar. We're going to do another example in the practice problems next class where I do this a different way, where we go to the Kb equation more like we did for the acids, so you'll see an example of that also. But this is a little different. So I'm going to clean this up top and get me a little more room for the rest of this. All right, so that means that my Kb, which is, where's my value? 1.8 times 10 to the negative fifth is going to be 0.0015 times 0.0015 at the top, because my concentrations of NH4 plus and OH minus are equal. And then we divide by X minus 0.0015. No quadratic risk here. So that's good. If I solve for X from here, which I want you to try, but I'm not going to belabor that, 0.01265, and that's going to be my concentration of NH3. So, almost, not quite. I still have to subtract, technically, 0.0015 from that to get 0.125 molar NH3. This was a little different than we've been doing, so I will, like I said, put up another example for tomorrow also.